Hello, Mr. True again. Back to do a part 3 of solving equations with log functions. After answering questions with my kids in my class, I realized I should be doing this. I should have done some examples where the log function was on both sides of the equation. So let me do a few of those for you. If you are uncomfortable with your properties of logarithms, please watch part 1 and part 2 of my solving equations videos. The link is right here above my head. Okay, when you have an equation where the log function is on both sides of the equation, you have two choices. You can move everything around so that you get both logs on the same side, or you get the equation set up so you just have that one log function on both sides, like this one is already set up as. Now, when you log a number, you only get one possible answer, a unique answer. So the fact that we only have one function on each side of a natural log, and there's nothing else going on, it's like, we have one function, natural log, which of course both sides have a base of e. So one math function, same base on both sides, so what we're logging on both sides must automatically therefore be equal as well. But to reemphasize the fact that exponents are the inverse function of logarithms, I'm going to show the actual step of making both sides of the equation an exponent of e. Now when you have these bases, these like bases stacked on top of each other, again, the log functions and exponential functions are inverses of each other. If they're stacked immediately, leading coefficients of 1, those common bases will cancel out, base of e and log base of e, which is natural log. So that step will cancel these log functions out, and we do get 4x minus 1 equals 7. And now we just have a two-step equation left to solve, which is add 1 to both sides, and then finally divide by 4. Now, what's very, very, very important with log functions, and actually whenever you're solving any equation with major restrictions on the domain, like square roots, if your variable's underneath the square root, you have to remember you cannot square root a negative number, or even root a negative number. If x is in the denominator, with your original equation, you cannot divide by 0. And with log functions, you cannot log a negative number. So, major restrictions on the domain. So when you get an answer that you think is the actual answer, if you do not remember to plug that back into the original problem and make sure that it does not make the original equation undefined, you are missing a very key and important step. So take the 2, plug it back in. 4 times 2 is 8, minus 1 is 7. That's positive. And of course over here we always have the value of 7. So indeed, when we take the value of 2 and plug it back into the original problem, we are able to work it out because we are not logging a negative number. So 2 is answer. It will check out and we're good to go. So first example done. Okay, second example. Let's take one that looks like this. Log of x plus 4 plus log of 3 equals log of 5x. Now here we have common logs, base 10 and not base e. And our major problem here is we have 2 logs on the left and 1 on the right. So we're going to condense these logarithms to have that one function on each side, that one log function on each side. And then technically we're going to make both sides an exponent of 10 to cancel out the log base 10 and finish up with hopefully a relatively easy algebra problem. So we have log base 10, or common log, of 3 times x plus 4 equals log of 5x. Now, we're going to need to distribute this 3 through the x plus 4 and get log of 3x plus 12 equals log of 5x. And now we do have that singular common log on both sides. No other math functions occurring. We have leading coefficients of 1. So we can make both sides an exponent of 10. And those exponents and those logs are going to have the common log of, or the same log, or excuse me, base of 10. So they will cancel out. We get 3x plus 12 equals 5x. I'm going to bring the 3x over with subtraction and get 12 equals 2x. Again, that was with subtraction. Divide both sides by 2. Get 6 equals x. And again, we must make sure that we're actually able to take that 6 and plug it into all of the logs that are in our original problem, and make sure, again, we're not attempting to log a negative number because those values are going to be undefined or no solution. And 6 plus 4 is 10. This is always going to be 3. 5 times 6 is 30. So indeed, we will be able to log these, and I'm pretty sure when you take that 6 and plug it back in, it is going to check out as a correct and valid answer. So, bam! Next problem. One last one left to go. That I'm going to do anyway. You might have a lot more in your homework. Okie dokie. Alright, so we got one last example of log of x plus 2 minus log of 2, again with the common log, equals log of 4x plus 1. Okay, let's see what happens here. Now, when you subtract logs that have the same base, you can condense those through division. So we have log of x plus 2 divided by 2 equals log of 4x plus 1. And again, we have now one log function on each side. The leading coefficients are 1. Nothing else going on. They both have a base of 10 because they're common logs. So we're going to make both sides of the equation exponents of 10. And we get x plus 2 over 2 equals 4x plus 1. We're going to multiply both sides by 2 and get, well, the 2's are going to cancel out, and we end up with x plus 2 equals 8x plus 2. We have an x on both sides, and we have a 2 on both sides, so we're going to subtract both sides by x. That is going to give us 2 equals 7x plus 2. Subtract both sides by 2. And we get 0 equals 7x. Divide both sides by 7. And let's make sure before I start yelling bam and celebrating that we can plug in 0. That's going to be the log of 2. We can plug in 0. That's going to be the log of 1. So indeed, we are going to be able to plug this back in and check the answer. Nothing is going to come out to be undefined. So I'm Mr. True. Bam! Go do your homework. Thank you for watching. I appreciate it very, very much.